Okay, let's get moving then. So continuing our exploration of MRI today and extending what we looked at in the previous lecture, namely gradients, pulses in the presence of gradients, evolution, acquisition under gradients, which makes our frequency location dependent, into a three-dimensional and, as a special case, two-dimensional situation. So to remind you what we had in the previous lecture, so item 1, again, motivation. We had observed that because Fourier transform separates out frequencies in our time domain signal, if we make those frequencies location dependent, Fourier transform will start separating locations. And we had, last time, a one-dimensional sample. So here's our sample in an MRI instrument. And what we said, okay, we've got some proton density of that sample. And if we make the magnetic field here location dependent, so that is our x-axis, that's a student inside the magnet. And if our magnetic field linearly varies across this sample, so that is delta V naught as a function, once again, of location, then the Larmor frequency with which the spins in our student process will be location dependent. And then if we record the NMR spectrum, the frequency of the protons in the fit will be lower than the frequency of the protons in the nose. And so, as a function of frequency, we will see exactly the same picture. So there will be our fit at low frequency, our belly at some intermediate frequency, and the head at the high frequency. This does, however, only work in one dimension. Let us consider a three-dimensional sample and think about what would happen in that case. So 3D, and let's take a look at some cubic hypothetical sample that we would put into there. So something like that, and our sample will be a cube here. So for example, extending like this, and then down here, and so we have our cube. If we were to make a gradient here, for example, in the x direction, that part of the cube here would have signals at lower frequency, that part of the cube would signal at higher frequency, but of course the perpendicular direction of the cube will all end up in the same place. So we would be able to resolve a one-dimensional picture, but we would not be able to extend it into the other two dimensions. Likewise, if we do a gradient with respect to y, different y coordinates of the cube will signal in different places, but all x coordinates for a given y will signal in the same place. And so we can record one-dimensional projections of our sample with this simple technique, but it would be very difficult to reconstruct the internal structure of the sample if we are only seeing the shadows on the wall, as it were. So we need to do something here that would allow us to be selective about which voxel here we are looking at. So the first item on our agenda today is therefore slice selection. So to slice selection. And we will start with the concept of a soft pulse. So item A here, soft pulses. Remember what we had with the Bloch sphere and all of those rotation diagrams that we had for the pulses a few lectures ago. We had our Bloch sphere, we had our magnetization vectors rotating on it, so Z, and let's say we have a magnetization vector that points originally in the z direction of the laboratory frame. When we went into the rotating frame, we could rotate this magnetization quite neatly into the transverse plane by applying a suitable radio frequency pulse with the correct duration, correct magnitude, and the correct phase. We did, however, assume that our spin was exactly on resonance with the rotating frame. That is, the frequency of the rotating frame was equal to the Larmor frequency of the spin. That is, when it was sitting in the transverse plane, because of the rotating frame, it was just sitting there and not moving, because our little web camera was moving at the same frequency with it. Consider, however, a situation like this, when we have a gradient, when different spins would have necessarily different frequencies. And so, as they are turning by the pulse, they will also be precessing around the z-axis. And so the trajectories here will not only turn, but they will also precess. And then, as we have greater and greater offsets from the resonance frequency, the spin will end up in different places. And actually, if you do the math, it turns out that it does not perfectly arrive into the transverse plane. It sits somewhere above it. So it terminates here, here, here. And eventually, when the spin is very far off resonance, essentially what happens is that this dotted thing just loops around, so like that. And the spin doesn't do much. It actually is sitting on the z-axis. In that case, it is said that we are very far off resonance, and the pulse is simply not influencing those spins. So, if we look at our frequencies, therefore, so that's the frequency, and we look at an efficiency of the pulse with a finite duration and finite amplitude, we will realize that it doesn't actually influence the spins very far off resonance all that much. They just sit there on the z-axis and wobble ever so slightly. So we have something like that. However, when we get closer to the resonance frequency, suddenly the pulse is very effective at turning it on to the xy plane. And as we move further away from resonance, we also just start getting the wobbles here. If you work through the math here, and it's quite complicated because we do have to solve those differential equations of motion for the xyz component of the spin, but the final answer for this is sine omega over omega, roughly speaking, so the sinc function. And what this tells us is, okay, if we take a gradient and we apply a pulse in the presence of a gradient, we will only excite the spins in a certain frequency window. Which of course means, since our frequency is location dependent, that we will excite only the spins in a certain location. And let us now look again at our little cube and think about what is going to happen. So, we put the gradient of the magnetic field in the x direction here. Here, on this side of the cube, we will have slower frequencies. Here on that side of the cube, we will have faster frequencies. But the pulse is only influencing the frequencies which are either in the middle or around some specific value. So only the spins that are sitting somewhere with a particular value of x will see that pulse. So that is also that value of x, then that here. And I think if it's there, it's somewhat behind, so we will have it like that. So we have that particular slice of the sample responding to the pulse. and all of the other spins will continue sitting on the z-axis like nothing happened. Okay, this is the first step in our attempt to do three-dimensional imaging. We managed to reduce the problem of imaging the entire three-dimensional cube now to the problem of imaging just one slice, because we put the magnetization inside that slice in the transverse plane, and so that can be detected, and the magnetization in the rest of the cube is sitting on the z-axis and doesn't get in the way. Okay, the problem of imaging this three-dimensional object got reduced to perhaps sequential imaging of two-dimensional objects, so we can repeat the experiment, have a different frequency of our pulse that will select a different slice, and so if we are able to image an individual slice, then by repeating the experiments for those slices, we will be able to acquire three-dimensional image. But still, now, even though we have two dimensions is too many, because that only permits us to image in one dimension. So we need to have extra tricks in our toolkit to be able to do the two dimensions. Okay, so item 2 on the agenda, or rather B, under the slice selection, is the concept of a gradient echo. Remember the spin echo. When we had a heterogeneous sample, spins in it precessed at different frequencies, and we had to take some special measures to recollect those spins, otherwise they just go out of phase and all signal is lost. So I will remind you what we did when we dealt with the spin echo. So let's put a reminder here. Spin echo. When we had our spins in the transverse plane, when they had very different frequencies, for example, as a result of a bulk heterogeneity in the sample, say you have a powder and then the magnetic susceptibility on the surface of a crystal is different to the magnetic susceptibility in the bulk, and so some spins will be precessing faster than others. So in the rotating frame we will have some spins being ahead and other spins falling behind, so they spread out in the transverse plane, and there will be some spins that stay on the x-axis of the rotating frame. So they spread out after we do a 90-degree pulse. So say this is protons. If we do a 90 and then we wait for a period of time, what will happen is these spins will spread out because their frequencies are different. However, we said if we do a 180, in either x or y, doesn't matter, I will do a 180 here with respect to x. What will happen is the faster spins will end up behind and the slower spins will end up ahead because the pulse has flipped them. So we will have the yellow spins now falling behind, the white spins remaining where they are, and the blue spins being ahead. But of course the blue spins are slower than the yellow spins, and so the magnetization will just recollect itself. And that will cause a burst of signal in the detector, and that's called a spin echo. Tau. What we'll see here, if we look in the detector, is our signal slowly fades. Then in here it will recollect itself and reappear, and then finally disappear again. And this burst of signal was originally called spin echo by Erwin Hahn, who invented this process. Let us now take a look at what would happen in the presence of a gradient. Once again, what is going to happen, so if we take our, so we draw a line here, we take a look at the proton channel again, we do a 90, but then we have the gradient channel as well. And after the 90, we will apply a positive gradient. What is going to happen is exactly the same. Our sample may be homogeneous, but we have created an artificial heterogeneity by making magnetic field different in different parts of the sample. And so there will be spins in the feet here that are slower, so they will be our blue spins. There will be spins in the nose, which are faster, they are our yellow. And eventually, if we look at the signal here, the signal would vanish. And this is in fact used in magnetic resonance to destroy unwanted magnetization. In many cases, for complicated experiments, it makes sense to destroy intermediate transverse magnetization because everything you want is longitudinal, and then there are special coils in NMR probes called HOMAS coils, and you just send some current through it, it goes boom, and all of your transverse magnetization is dephased and obliterated, which is kind of handy. But in our case here, we want our magnetization back, please. And so what we can do is apply a gradient with the opposite sign, simply by sending a reverse current through the gradient coil. And of course, what is going to happen is, because the signs are now reversed, the spins in the feet will become faster than the spins in the nose, and the magnetization will recollect itself again. So like that, and reappear with the same magnitude at the end of this, and this is called a gradient echo. And that is necessary because in our slice selection process, notice what had happened. We put the gradient of the magnetic field. We have achieved our slice selectivity. We have put our spins in the transverse plane. So all very good. But of course, we now need to compensate for the dephasing that has happened during this gradient process. And so in a lot of magnetic resonance experiments, when we are doing a stage which involves a magnetic field gradient, there is an extra stage before or after that refocuses the offsets that these gradients have caused, right? So-called gradient echo stages. All right, so after all of this is done, so we have done the slice selection, we have done the gradient compensation here to make sure everything is pointing in the right direction at the right phase. You will see the sort of picture that is given in the figure 2 of your handout. This is a simulation, in fact, using the software that we are developing here in Southampton. So you can see a three-dimensional proton density map of the brain here, and then an oblique slice through that brain. And this is literally a sync pulse like that being issued in the presence of a gradient, and then the refocusing stage here puts all the magnetization in the same direction within that slice, and we can press it. Okay, so we have created our slice and we have tidied it up. The next stage that we need to go through is detection of that slice. So stage 3, 2D MRI and phase encoding. Remember K-space. It was the space of spiral windings. So if you have a gradient spiral and it is tightly wound, then that is a large value of K, and if it's weakly wound, it's a small value. And that was our map that Fourier transform accomplished between the space of these gradient windings and the physical imaging space. Now we need to do that in 2 dimensions. So how would we accomplish that? Let us start separate board here, drawing our final ultimate MRI pulse sequence. And that is still, of course, the simplest one there is. The real clinical ones are much more complicated, but that's the simplest fully featured MRI pulse sequence. So imaging sequence. Okay, we have the proton channel on which we would have our pulses. We have 3 gradient channels. We have the gradient in the original slice selection direction, so GSS, and there will be a channel here. And we have gradients in 2 perpendicular directions. So if our slice selection was in X, our slice in the Y is in the YZ direction. So one is called phase encoding, and I'll explain what that is in a moment, and the other is called frequency encoding. And that will also be explained. Okay, the first thing that we've already done is we have turned on the slice selection gradient and we gave it a shaped pulse. So there will be a sync pulse here. And that has selected our slice. But it has messed up the phases within that slice. And so what we must do is a gradient refocusing stage here. And it actually needs to be shorter than this one for complicated reasons to do with the fact that the magnetization spends some time longitudinal and some time transverse. But what this is it brings our slice in the correct phase. Okay, so this is slice selection. Now, we need to sample our K space, but remember how we sampled it. We turned the gradient on and then we ran the acquisition. So simple 1D, I'll put it in here, so reminder, 1D imaging. That was just a 90 in the presence of a continuous gradient that made the frequency location specific, and we had our signal in here, and these different points of that signal were the K space points. So K points. Now we have 2 dimensions. Now we can do that, of course, and we will do that, but we also need to sample in the perpendicular direction. But what these gradients accomplish is, because this K is minus gamma GT, incrementing the gradient or giving a gradient pulse moves us in the K space. So what we do is a repeated experiment. We say, okay, we run this multiple times. I mean, the patient is there in the magnet, he's not going anywhere, right? So we can just run the experiment several times. And we will run the first experiment with a tiny value of this gradient. And because these gradients do not talk to each other, they can actually be simultaneous. So for a little bit of time saving, right, it would have been here, but it can be shifted here just to make the sequence a little bit shorter. Okay, so what this will do is it will shift us. So let's say this GSS was in the X direction. Let's assume that the phase encoding gradient, however, I put it in the handout here, just to make sure I've matched the notation. Yeah, so this is Y, and that is Z. So, and then the K space we have, therefore, is KZ and KY. What this little gradient blip is going to do is it will shift us up with respect to the KY. It'll accumulate a little bit of KY. Right, so it'll wind the sample up in the Y direction ever so slightly. Okay, what we'll then do is we will run this usual imaging process. Magnetization is already transverse, so we don't need to put it transverse. But remember this gradient echo business. We need to have the echo in the right place. So what this G phase encoding does is it needs to pre-roll itself. So it's a slight negative block here, followed by a positive block, which is continuous, and acquisition. So at this point we detect our signal. So let's have a signal channel here as well. And so at the point when that gradient goes into positive, we start detecting. And of course it's been dephased here, so it will come and get rephased and have a blip around here, and then it will get dephased again. And we will sample that with some frequency, which we will discuss in a moment. So there will be these points here. And those points, the yellow ones, become the points in that direction, because the final gradient is on the z-axis. Then we just turn everything off except the magnetic field, and we allow all of the magnetization to relax, and that takes a couple of 100 milliseconds. Then we restart the entire experiment. We do the slice selection, and then the phase encoding gradient, we make it twice as big. What that does is it winds our y direction a bit stronger and puts us on a different line here. Then the frequency encoding gradient and the acquisition is going to do its job, and we will record the second set of points. What we will then do is repeat the experiment again and make this even stronger. And then of course we can keep on going. So this is the notation for it. And of course we also need to sample the negative direction. So like that. So this is an incremented gradient, and its role really is to do exactly the same as this thing does. But because our physical reality unfortunately only has one time dimension that we can travel in, we can only record one timeline in a single experiment. And so if we would like to record multiple times, right, so one time dimension in there, the other time dimension in there, we unfortunately need to repeat the experiment and increment that time indirectly. Okay, and so we have thus sampled the two-dimensional case space. So all of that goes there, there, there. And this explains why MRI imaging is quite a slow process. Hands up if you've been inside an MRI machine by now. There you go. So 15 minutes or so. Yeah, or longer, depending on what exactly it is doing. But you can see that if a single run through this is a couple of 100 milliseconds, for sensitivity reasons it needs to repeat it several times. So let's say, you know, a few seconds per the direct dimension acquisition, and then perhaps a couple of 100 indirect dimension slices. Then yeah, it's a few minutes. And then what will happen, of course, is now that we have a two-dimensional case space representation, a two-dimensional Fourier transform will give us the image. Right, so some, I don't know, animal sitting there, not doing much. Okay, so this is the basic principle of MRI in 3 dimensions. We have, as you can see, to be quite clever with the 3 gradients. We have to put in those echoes, and the result is shown in figure 4 of your handout. So you can see in the left panel of it, repeated acquisitions through the K-space, and you can see the white spot which corresponds to this echo here, and then the Fourier transform of it produces us a nice brain image. You will, however, notice, if you look very carefully at that picture, that a little bit of that brain got clipped off the bottom, and it had reappeared from the top. And this is the same Nyquist-Shannon sampling theorem that we have discussed when we dealt with sampling of NMR spectra. So let us cover the final topic for today, and that is K-space sampling, and that's topic number 4. So remember our discussion of time domain sampling of a magnetic resonance signal. We said, okay, assuming we have some really fast frequency, so that is some magnetization and that is time, and if that is a rapid oscillation, then we'd better take care to sample this properly, because if we sample it at intervals that are too long, so say here, 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 and there, right, is clearly fewer than 2 points per period of this oscillation, what of course will happen is the mathematics will misinterpret that frequency as a lower frequency. And so what happened with that unfortunate brain in your picture is, under the gradient that we have supplied, a corner of that brain, because it's so far from the center, ended up in a very strong or very weak magnetic field, resulting in its frequency being outside of the sampling window, and then the Fourier transform had mistaken an undersampled high frequency for a much lower frequency, and so that little corner of the brain got reflected into the low frequency region. So clearly there are minimal sampling requirements, and it's the same old Nyquist-Shannon theorem, so 2 points per period of the fastest oscillation is necessary to reconstruct the signal without any loss of information. Now, let's take a look here. There are 2 properties here that we can see. One is the spacing of these K points, so that, and we will call it delta K. This is how densely these K-space points are positioned. And the second property is the overall extent that we have sampled. So it's that entire thing from here to here. And we will call it delta K. And these 2 parameters determine respectively the size of the real space image and the resolution of the real space image. And because the K-space is reciprocal to the physical space, it is exactly the same relationship as you have in crystallography. I don't know if inorganic chemists have touched upon X-ray diffraction yet. They have, and there you also have a K-space, and there you also have resolution. And in fact, the concept of all of those lattices, reciprocal lattices, are identically repeated here, except their physics is discrete and our physics is continuous here. So, by the same argument as what they have, and you can work through that by just looking at the Fourier transform, the resolution, so delta x, so that's resolution of the image, is determined by the total extent that we have acquired in the K space. So that is 2 pi over delta K. So that is point spacing. how closely the points are spaced, and that is the total extent of the k-space sampling. So the more we sample of the k-space, the greater the resolution is going to be. And if you look at figure 4 of your handout, I have the same brain, which has been acquired with a lot of points in the k-space, so large extent, and you can see on the right there a nice high-resolution brain. And then I've artificially shrunk the k-space down by just multiplying the sides with zeros, and you can see the brain got blurry. So that is the relationship between the resolution and the extent of the k-space. Then, of course, we also have the extent of the image, right? So this here is the extent of the image, and the minimum resolution here is delta x. So likewise, reciprocally, the size of the image is 2 pi over delta k. The finer the point spacing in the k-space, the greater the frequencies that we have digitized, the greater the location range that we can therefore reproduce. Right? So that is the size of the image. And these two are quite important. Now let us think about what determines these parameters and why MRI instruments tend to be expensive. So firstly, let us think about what determines the resolution of our picture here. We want to make delta k as large as possible, because that makes for finer pixels, right? Delta k is the pixel size. But what determines delta k? Well, delta k is determined by k max, right? The maximum k that we can achieve. But what is k? K is minus gamma gt. Gamma we can do nothing about. Interestingly, T max, right, so that's K max, we also can do nothing about, because the magnetization inevitably relaxes. It has a T2 time, and the T2 times are in the hundreds of milliseconds, and so the longest T we can afford to sample before the magnetization is completely lost is also fixed. And so the only thing here that allows us to make this k bigger is the gradient amplitude. Means we have either to have more loops in the gradient coil to increase the induction, or we need to have a greater current through that coil. Both mean a lot of engineering, high precision engineering, because these gradients have to be extraordinarily precise. Remember, 3 Tesla, right, is over 100 megahertz. So you are talking time scales of microseconds to nanoseconds on the precision and the fractional accuracy of all of the electrics that goes on into that instrument. So the stronger the gradients, the higher the resolution the instrument is going to have. But at that point you hit very physical limits. The derivative of the magnetic field appears in Maxwell's equations. The moment you have a rapidly varying magnetic field, outward pressure is exerted, mechanical pressure is exerted on the gradient coil. And so the banging sound that you hear when you are inside the MRI instrument is in fact the Maxwell pressure trying to pull the coil apart when a very strong current is sent through the gradient coil. So there are firstly electrical limits on how strong a current we can send with what kind of precision, and secondly a purely mechanical limit of how much abuse, mechanical abuse, such devices can handle. And finally, of course, any varying magnetic field creates inductive currents inside your tissue, and at some point if the gradient's too strong, then the nerve cells begin to fire because induced currents become too strong. So certain strengths of the gradient is incompatible with a living biological organism. So very, very, very high resolution anatomical MRI images are unfortunately invariably conducted on the organisms who are dead and don't mind anymore. So that is what determines the resolution. Then, of course, the size of the image, that's straightforward, right? We simply need to have more points acquired per unit time in the K-space, so we just need to make it denser, but that comes at the cost of sensitivity, because the digitizer runs at full throttle every time anyway, so it puts them very, very, very densely, but then it averages nearby points out to reduce the noise to the sampling levels that you realistically require for the size of your image. And so reducing delta K in the acquired data means a bit more noise is going to get through. So there are these various trade-offs that we must be aware of. And I think that's me. So the summary of the lecture is our very simple picture that we have started with, saying, okay, one-dimensional sample, stick it into a magnetic field gradient, frequency becomes spatially selective, Fourier transform will resolve us all of the spatial locations. This picture becomes a bit more complicated when we have to deal with a three-dimensional sample, because this can only record as a 1D. So on a three-dimensional sample, we have to do it in stages. First, we need to only excite just one slice, and then we need to acquire that slice in a complicated, concerted way involving all three gradients. And this is how we do it. Firstly, we notice that as in any spectroscopy, the transition is only influenced by the electromagnetic radiation of the same frequency. So if our spins are off resonance, they will not be influenced by the pulse. More precisely, after a lot of mathematics, if you do a rectangular pulse, so finite duration, finite amplitude radio frequency pulse, the excitation pattern with respect to frequency will look like a sink. Those of you who did perturbation theory in quantum mechanics will remember exactly the same story coming out of the derivation of the Fermi golden rule. At some point you will get there. It also has this sink function in there, which eventually collapses into a delta function that then goes into the Fermi golden rule proper. Okay, but we can do slice selection by applying a gradient in one direction, then a pulse, and so every spin with that particular value of our gradient coordinate will get excited, and therefore a slice. Then we have to make use of the gradient echo. We've had a gradient on for a while. We need to have it on in the opposite sign for a while to just recollect all of the spins in the transverse plane in the same place, so we can continue manipulating them. So that is our shaped pulse, that's our slice selection gradient, and that is the compensation gradient with the negative sign. Then what we do is we realize that our K-space is now two-dimensional, but we can still sample it because gradients move us in the K-space, because a gradient makes our spiral winding tighter or looser, and the tightness of the spiral winding is in fact the K value. So we can repeat the experiment multiple times when we have different values of this encoding gradient. This is why it's called encoding gradient. It encodes the indirect dimension of the K-space. And then we can do the gradient echo acquisition, so we defocus it and then turn it on in the opposite sign so that it refocuses. The signal blip happens in the middle of the K-space image and then defocuses again, and you see the examples of that in the handout. Assuming we have done all our sampling correctly, the two-dimensional Fourier transform will get us the image. The two parameters of the image are size and resolution. Size is determined by the closeness of the points in the K-space. The finer the spacing, the greater the frequency we can digitize, the greater the range of locations we can reproduce, the greater the size of the image. And the resolution is determined by what kind of frequencies we can separate. Right? The stronger the gradient, the stronger the separation of the frequencies, the greater the resolution. But there are electrical limitations to do with the gradient strength in there that puts the limit on the resolution. And because this delta K is a trade-off with the signal to noise, the image size has to be traded off against the amount of noise you can have in that image. And spin spectroscopies are really quite insensitive, even though they operate at the absolute electrical limits of sensitivity that one can reasonably have in a physical device at room temperature. All right, I think that's all I wanted to say. Any questions?